Okay, so the wizard problem. Trying to summarize and spoil. Maybe we'll try to get you guys to figure out some last bits. Okay, so remember what the wizard problem was? You have like 300 wizards, right? And they have 25 different colored hats put on them. And you know the numbers of their hats, the colors, there's exactly 0 of one color, 1 of another color, 2 of a third color, and so on until 24, okay?
Yes.
So there's 24 of one color. And the object is that they all guess a color simultaneously, and you want to guarantee 150, okay? So if you look at the point of view from one of the wizards, they can basically tell they're not any of all the colors but 2, so they're down to like a 50-50 guess at worst, okay? But remember, you can't just say it's 50-50 and then you can't guarantee 150, because that argument also says you can't guarantee anything, okay? So and our journey has been that we could guarantee 1 out of 3 at first, 3 out of 6, 5 out of 10, and then yesterday 78, huh?
25.
Yeah, and then 145, yeah. So quite amazing. Okay, so let me just quickly recount the strategies again. So basically, if there's only, so if you have an even number of wizards, they're picking between their, like what they see as the other 5 wizards as colors, and possibly the colors of the 5s. Okay, so there's one less odd number, and they don't know which color they are, so they don't know which color has the even number. But came up with a strategy to always guarantee half of the evens, right? So that strategy was you always pick left mod 2. So if you take the point of view of one of the wizards, you mod 2 all the other stuff, and you pick the thing on your left, so you get the white, you know? And so in this way, if you do that for all the wizards, okay, so picking left this time will give you a black. So this one will pick right, wrong, and this one will pick right. And in this way, you can kind of pair them all up so that half of them are right. Okay. All right. And so then there was another. This is actually Leo's contribution to the odd wizards. Quite a feat. If you have odd and even instead of even and odd, you get everyone to ignore the lowest numbered. So you number them all, like I did here, and get everyone to ignore the lowest number from each color. Okay. So, yeah, and while none of them will be sure what they got, like none of them will be sure if they're actually the lowest or not. All of them except for one person will carry out the strategy correctly. So all of these people will eliminate these 2, right? And they'll carry out the correct strategy for being even. Yeah. Okay, so that's how you get to 144. Okay, and then 145 was combining 1 and 3. Okay. Okay, so now Will suggested an idea, which I claim actually works. So if you have, maybe, so if you have 5, so maybe I put 1 and 3, yeah? Yeah. So the 1 and 3, if you pair them together, right? Okay, so maybe if you want to still contribute to getting this at the end, 5. Different shape. 7. So you pair the 1 and 3s together, yeah? The 5s and 7s together. I think it actually doesn't matter which you pair together as long as it's 2 odds, yeah? And luckily, out of 24, there's an even number of odds. So basically the goal is to pair them together, right? And somehow recover the votes of the useless people, yeah?
Somehow.
Yeah, so maybe I can give you an example. Yeah, so we actually kind of discussed this yesterday as well. But I think we were too dead to act on it. So, is it obvious that everyone has a switcheroo strategy? So like,
Switcheroo.
so basically it's the same situation with 1 and 3, right? So the 1 guesses based on whether they think the 3 will succeed or not, right? So if the 3 has 2 out of 3, then the 1 will guess something, right? If the 3 does not have 2 out of 3, the 1 will guess the other thing. That's how it was working before, right?
Yeah, everyone knows that.
Yeah. So can you see the 3 now? What they would do is now they would look at A and based on their color sort of do the opposite of what A does, yeah? So if A picks like X, then when A sees dark it picks X, right? Then the 3 must um pick non-dark when it sees A has X. Yeah? That makes sense? Yeah. So and then we'll even suggest this. So it's not that they pick differently. It's that they have 2 strategies. Yeah. So the 2 strategies need to be negations of each other. Okay. So for example, like A knows how this is going to turn out if they. So there's 2 possible strategies. One strategy and A counts that strategy and sees if it's going to be successful. If it is, it picks X. Okay. If it fails, it's Y. Yeah. Okay. So it just so happens that anytime you have a strategy that fails, so fails, it's not 0 and 3, it's 1 and 2, right? You can convert it into a success by doing the negation of it. So, do you know what I'm talking about?
Yeah.
So you just do the opposite of what you're gonna do. You know? So like failure means it's like cross, tick, cross. You know? If you switch the strategy, it'll be tick, cross, tick. That makes sense.
Yes. Yep.
Yeah. So actually, in this sense, you can even do. So you don't have to do the picking left strategy that we had before. You can do the modified strategy for odds here as well, right? So you just okay, should I spell it out? So what you basically do is see the odds strategy, you guarantee half of the people that actually know what's going on, right? Or they they don't necessarily know, but they're doing the right thing according to what's going on, yeah. And then there's one guy who's kind of a bit lost, yeah. But even though he's lost, he still gets an outcome, right? So he can guess it right or wrong.
Yeah.
So some of the time he might even be right, yeah. Some of the time he's wrong, yeah.
Okay.
But the other people can know if he's going to be right or wrong. They can see the whole situation.
Yeah.
Okay.
So what would be like a good or bad strategy for the like good or bad strategy at which you do the negation?
Yeah. So for example,
So if it's 5 and 7, the fives look at if the sevens have a
yeah. So if it's 5 and 7, right?
wait what?
There's 7. Yeah.
But that's meant to be 5 and
Oh.
7.
Okay. 4, 7 and 6. Yeah. Okay. So
So we need a pair of the 5 and 7.
the 5. Yeah. We pair these up. Yeah. Okay. And notice they both have obvious strategies to employ. Yeah. So strategy. So let's just call them the left or the right strategy. Yeah.
Mhm.
So this is the left or right strategy. Yeah. And this is the left or right strategy. Yeah. Like what is the left strategy? Yeah. The left strategy is they delete the two lowest. Yeah. And carry out the guess left mod 2 strategy for evens. Yeah? What is the right strategy? Well, you just do the same thing, but you guess right. Yeah. So can you see the right strategy is the negation of the left strategy?
Yes.
So what that means is if you're gonna get not
Wait, shouldn't the negation be like you guess the opposite of the color with 2 to the left?
Yeah, which is
yeah, it'll be the
Yeah.
case in the other one. Yeah. Yeah, so I guess you don't have to actually claim it's the right strategy as long as you just guess
It's
the
opposite
negation.
of
It's the
left.
negation. Yeah. But it's kind of nice that the right strategy is the negation of the left strategy. Yeah.
Yeah.
Yeah. So basically, what you have is you have a choice of two strategies, right? Which guarantees you two outcomes. So if the odd one out is guessing wrongly, right? If you negate the strategy, he'll guess correctly. You know, it's just you can't guarantee that on your own, right? I think this is enough for people to figure this out now. Anyone want to prove it's sufficient? Demonstratum.
Construction. Let's make construction with 300 wizards.
What?
What?
No, it suffices to do this case, okay?
No.
It's ST introduced this.
It's more fun to have a construction with 300 wizards.
Does this make sense?
Yeah.
So basically, each group of odd wizards have two choices of strategies, yeah? This is what we were talking about. And the strategy guarantees, so there's 2k plus 1 wizards. The one strategy gets you 2k or k, and the other strategy gets k plus 1, right? You just don't know which is which. Okay?
So like one of the like say the sevens,
Yeah.
they choose left if the top picking left is good.
Yeah, so
Okay, and they pick right if the top picking left is bad.
so let's see. So let's call this 5-4, yeah? Let's call this 7-6, yeah?
Yes.
So what is the 7-6 decision process, yeah? So assume 5-4 is left, yeah? Counts correct guesses, yeah? If correct more than half, yeah? then guess left. Yeah.
Yep.
If less than half, guess right. Yeah. Makes sense, right? And then, so what's the 4-5 strategy then?
Same thing.
The opposite. Okay. So assume 7-6 is left. Yeah. If correct, greater than half, guess right. Yeah.
I guess right.
If it's less than a half, guess left. Yeah.
Wait. That's different from the 7-6.
Yes, the opposite.
Yes, it should be the opposite. Yeah.
Alright.
So can you prove that this will work?
See. Each strategy has a minimum of k minus 1 all divided by 2. And then since they're doing different strategies, and at least one of them has k plus 1 divided by 2, then that gets to 2k.
Wow, Lucas. Starting on the floor. The first hour.
Oh.
Oh.
Wow. Very good.
Yeah. Yeah, so basically all you have to really look at is the odd guy out, right? The lowest numbered guy to guess, to know if it's going to get more or less than half, right? Because everyone else is going to cancel. So they can do it very quickly. So if that's like the lowest guy, right? And this is like the lowest guy.
Yeah.
They just need to look at them to see if it's like greater than or less than half, yeah?
Well, we don't really care how quickly they do it.
Yeah. Just saying, like,
But they can just check on them.
yeah. So it sort of is just like a single person strategy in some sense. Because it really just look at one guy's hat, yeah? Okay. Yeah, because some people might not be convinced that they could count everyone's colors, but whatever.
No. They have unlimited time.
Those are unlimited brain.
Okay.
How they
Okay, so
figure
the whole
out-
point is like you wanna do what the other person you wanna be right when the other person is wrong, yeah? As long as one of you is right, you're gonna get half exactly. You're gonna get at least half. So basically, so 7-6 assumes the other people are doing the left strategy, yeah?
Yeah.
Okay. He could assume right as well. It doesn't make a difference, yeah?
Yeah.
And then if they guess half correct, he does something. It could be anything, you know? So it's basically arbitrary, yeah?
Yeah.
Okay, so if the other people are guessing more than half right with left, yeah? Okay. And so if they pick left, then you're good no matter what, right? Okay. It's in case they pick right, that's when you're stuffed, yeah? Okay. So I guess when they're correct or more than half with left, they're also incorrect is less than half with right, yeah? And if they're less than half with left, then they're actually more than half with right, yeah? So the time that they're going to be, wait, I should say correct, not incorrect. Yeah, so 5-4 looks at the strategy and is like, okay, well, let's have a look what happens with J7-6, what they're doing, right? So they're gonna so if I look at the 7-6 people and I see that they would have guessed more than half picking left, right? Then I want them to pick left, right? Okay. So so I want them to pick left when I'm gonna be wrong, yeah? I'm kind of saying this a little convoluted, but so 7-6, yeah, okay, so the 7-6 just fixes their strategy first, yeah? And then 5-4 knows what 7-6's strategy is, right? So this is maybe a better way to, or conceptual way to check it. So he looks at 7-6 and is like, 7-6 is if 7-6 is picking left, it's going to be correct more than half the time. Okay. So if that's the case, okay, then I want 7-6 to be picking left, right? 7-6 will only pick left if I am correct more than half the time with left, right?
So you do the.
I'm confused a little bit.
So you do the guess right. Then.
I think the easiest way to
Yeah.
check it is just to like check each case.
Yeah.
Oh yeah,
exactly.
okay, yeah. It's easier to check it once you've written it down. Yeah.
Well, there's only like 4 cases. So
Okay. How about this?
both are left, both are right. 5-4 is left, 7-6 is right, and then
Yeah.
7.
But I guess I wanted to say how I came up with it, but then like it's not working right now for some reason.
It's like the same logic as like the just
The two people, yeah, exactly. So let's look at the table of possibilities.
All right.
So we could do left. What was the strategy? Left is greater than half, yeah? Or left is less than half, yeah?
Mm-hmm.
Ugh. Yeah, let me just try to figure that out again one time. So you know that 5-4, so 7-6 knows that the other people are doing something if they're good, right? So if they're good with left, so if 7-6 is good with left, then 5-4 is gonna guess left, right? So you just need to see if 5-4 is gonna be so if you're doing good with left, they're gonna guess left. So you want 5-4 to be doing good with right. because in that case, if they're doing good with right, then they'll be doing so when they guess left, it doesn't matter what happens because you'll already be doing good with left, right? And when they guess right, then and you're not doing good with left, right? You'll be doing good with right, yeah. So yeah, so you want to cover the case that the other one that you might not be doing good at, right? So if you're doing good with left, they're gonna guess left.
When you guess right.
So you don't care what happens when they oh, I'm kind of confused again. Well, did what I said just make sense?
Yes.
Yeah, so 7-6 knows that if it's gonna do well with left, the other person's gonna guess left anyway, yeah? So it's only when they guess right.
You just assume that they will guess
Yeah,
right.
so when they guess right, that's when you're not gonna be doing good with left, right?
No, that's when you're going to be doing good with that.
No. When they guess left, their condition is if you're doing well with left, they guess left. Yeah.
Oh, wait.
Okay. So if they're guessing right, yeah, it's because you're not doing good with left. Okay. And so that's okay if they're actually going to do well with right. Yeah. So you look at them and you think, oh, okay, if they're not going to do well with right and they're going to guess right, well then I'm going to have to do well with right. Yeah, because I'm going to do badly with left. That's why they guess right in the first place. That's why you're going to guess right if they do well with left. So actually, the motivation is that they're doing well with left when they're doing badly with right. Yeah. So if they're doing badly with right, that's when you have to step up. Okay. So if they're going to guess right, that means you're going to do well with right. So because you know that, you can just comfortably guess right. Yeah. And you actually know that they'll fail and you'll succeed. Okay. Yeah. That's really it, isn't it? So
Actually, possibly.
So there's 4 cases. There's fails with left, fails left, fails left, succeeds left, succeeds left, fails left, then succeeds left, succeeds left. Yeah? Okay, so just test these cases. So if they're failing left, it's obvious to the other person they're failing left, right?
Yeah.
So then this person, upon seeing that the other person will fail left, so the 5-4 strategy basically just assumes they're doing left. If successful, picks left. If fails, picks right, yeah? So he looks at the other person. Okay, it looks like he's unsuccessful with left, so he's going to pick right, yeah? Right, and then left, yeah? And the other person does the opposite. So he looks at the fails left, and instead of picking right, he picks left. Succeeds left, now picks right. And then fails left, picks left, and succeeds left, picks right, yeah? That's the table. And you can see in all cases,
Yeah, that's at least good.
in all cases, here, if it fails left, it's going to succeed right, yeah? If here it succeeds left, it's gonna fail. If it fails left, it's gonna succeed right. Yeah.
There's like a faster way to make the argument. It's like because their strategies are opposites of each other, right?
Yeah.
If
Yeah.
they see opposite things, they will guess the same thing. If they see the same thing, they will guess opposite.
Oh.
So when you see opposite things and you guess the same thing, you're guaranteed one. If you see the same thing and you guess opposite things, you're guaranteed one.
Oh.
So you're guaranteed one no matter what.
Okay. Yeah. So that's that. So basically, that's another way of seeing it. So if you have, so it's like A plus B and C to D, and they always make sure if they're seeing opposite things.
Well, it's kind of like it's like A and B and A and B. Kind of.
Yeah. Okay. So if they're seeing opposite things,
They will guess the same.
they're
But
trying
the
to guess the
strategy-
same thing. Yeah.
Yeah, because the strategies are opposite. So
Yeah.
if they see different things, they'll guess the same.
Oh, very good. Now see the same thing,
They'll guess opposite.
they'll guess different things. Yeah.
Yeah. If you
Very
look at
good.
things, they will guess the same thing. Yeah.
Yeah. So it's kind of funny because it's hard to understand just combinatorially, but like
How do you
but it's
figure
also
this out
hard.
in 5 hours?
It's also hard to figure it out using conceptual. Like logic has always been this fine line between making a truth table and actually thinking about how things work.
Yeah.
How do you figure this out in 5 hours when you need to do other
I feel like
questions?
this is probably a 10 or 12 mark question in hindsight. But the thing is, like, you never know, like, how people can think of it quickly. Like, because, well, the thing is,
there's only like two main ideas really. Just the even strat
yeah.
and then like pairing up odds. That's about it.
Well, you can pair up evens as well. You can just do the pairing strat for anything.
Okay.
Ah,
Yeah, but
I don't think it's the
it
same.
doesn't really help though.
Yeah.
Yeah, so that can be done with any two odds, right?
Yeah.
Yeah, so that is guaranteed 150 wizards.
Alright, so we guaranteed 150.
I feel like it's harder than the JA6.
Well, it is SA6.
Well, JA6 was worth 10.
That's scary.
Was this harder than SA7? Sure.
It was definitely harder than Part A, but
Puppies is a whole different story.
the puppies are mystery. And Part A was only 6 months, so it's
Oh. Yeah, so I guess there's another lesson maybe to be learned here.
Fundamental theory of
Yeah.
sweats.
It's about persistence, yeah, you see? So this problem looked impossible to us. Would you agree with that?
Yeah.
yeah.
It looked impossible at the start.
We thought the answer was impossible.
Yeah. But we persisted with it, yeah. And eventually we got to the solution.
Right, now we make a construction.
No, you have to appreciate this point because a lot of the times, I mean, even I see with some of your EGMO problems, you just abandon them, right? So in the Tournament of Towns, like, you can abandon this problem, yeah? It's designed to be possibly abandoned. That's why it probably can be put on the test with such high variance in solvability, right? Because you can just abandon it.
Yes.
But like, say in IMO and stuff, you can't abandon the questions. Yeah? It's more like the questions are abandoning you. Okay, and so there's this fine line between doing problems that you enjoy, yeah, because it's a fun problem, and sort of being corrupted to the idea that you only enjoy things you're good at, okay? So as people who want to be good at stuff, inevitably you need to do stuff you're bad at to get better at them. Okay, and if you kind of keep avoiding this, it's not necessarily bad, right? You just become a specialist, right? And it's a very natural path for a lot of people. It's just it's incongruous with your goals sometimes. You know, like for example, like if you want to do well in the IMO, for example, which may or may not be a good goal to have, but if it is a goal that you have, you can't just abandon geometry, right? Like you can't abandon a topic just because you don't like it. Or you can, and you have to accept the consequences, right? So like, yeah, maybe you're just hoping to get lucky in the exam. That there's no geometries in six.
Mine was like 2-1 geo.
So even though there's a geometry question in every single problem 1 and 4 in like the past 20 years, maybe they'll be replaced by an inequality next year.
No, surely not. Surely not.
Okay, inequalities.
Yeah,
Inequalities are actually something I will abandon.
Bad.
yeah.
I thought you liked inequalities with this.
No, I do not.
And also notice the problem kind of fell like the persistence wasn't particularly like you don't have to be like a genius, right? It was like kind of obvious steps, you know? Like do the 3 case, the 6 case. Like these things that I think anyone could do, right? It's just that you have to do them in a row and keep doing them, right? Does that make sense? So maybe for the next segment. So for the next segment, we might have to. Okay, let me talk about the next segment in another video. All right, so that was the 150 wizards out of 300. Yeah, probably the best you could do. I don't know. Probably. See, if you could also start a research project and prove if it's the maximum. Yeah.
Or computer bash everything.
Yeah. Well, that's possible too. Yeah.
How do you computer bash like strategies?
Functions. Yeah. Yeah. So this kind of perseverance, I think, is kind of important. It's often mixed in with the competitiveness, right? You just don't give up on the problem, right? We heard about that talk where that gunning guy didn't give up on a problem for like 2 years. Yeah, so yeah, and we were actually only a little bit off. Yeah, we almost solved it last time as well. It's just a matter of actually unfolding the ideas into a solution. Yeah, in hindsight, it seems kind of easy to sketch the solution, right? Define even strategy, modify it to odd strategy, couple odds, and you're done. Yeah. So maybe that's why they assigned it only 8 marks. I'll raise the issue when I send more scripts in. Yeah. Any questions?